complex algebra and AC quantities. Now we know that a complex number consists of two parts. One is a real, another is an imaginary. Let us consider a complex number 2 plus I3, whereas 2, this is the real and another is the imaginary part, where I is square root of -1. Exactly in the similarly, AC quantities can be expressed in terms of complex numbers, and only difference is that we'll express instead of I, we will express with j. Therefore, you can say j square is equal to -1. Now, how and where it is being utilized, we'll see now. Now, let us consider a RLC circuit has been supplied by a voltage V and with a frequency of 50 Hertz. Now, already we know that if we know the inductance, then we can find the inductive reactance with the formula. You can see this is the formula we know. Only thing is that in this case we'll put a j before. That means it is an imaginary part of a impedance. And exactly in this case similarly, we know that in case of a capacitive reactance, we'll put minus j before. And we know that to find out 1 by omega c, we can find out with this expression. Therefore, again I repeat, for inductive reactance will plus j, and capacitive reactance is minus j. And then let us consider one simple example. Suppose this voltage V equal to 500 volt and resistance is R 200 ohm and L is 1.5 Henry and capacitance is 20 microfarad. And as we just now discussed, we can find the XL with this formula, and you can see the XL is found to be J multiplied by 2 into pi. I have taken 3.14 and 50 Hertz and 1.5 multiplied, and then J of 471 ohm. Now, in the similarly, we find the capacitive reactance also, but it is a minus j, and it is found to be this much, minus j 159.2. And already I told that resistance is the real part. Resistance is the real part, that is 200, and reactants are in imaginary part. Therefore, if you ultimately we get this, that means in this circuit 200 is the real part, which is the resistance, and 311.8 is in the imaginary part, and 311.8 is the inductive reactance of the circuit. And that form of presentations already we know in the complex number is called Cartesian or rectangular form, and from the rectangular form we can convert into the polar form, that we also know. But it was a recapitulation of that. I showed you that the magnitude we can find like this, and the angle we can find like this, and that is the polar form. We know that the complex number is this. And then we can find the I. We can find the I with a very easily, that I is equal to the voltage divided by the impedance. And now in the vector form, the voltage we are taking as a reference. It is a 500 and 0. Why we put 0 degree? Because voltage we are taking as reference. Therefore, after, and then whatever we found here, the impedance we are dividing, and then the complex number, it is the magnitudes are divided and the angles are subtracted, and from numerator to denominator, that and as a result the current we are finding that 1.35, and the angle and the phase difference we are finding with the voltage with this, and that is in the polar forms. Now we have seen how to convert the rectangular form to polar form, but now we'll convert it, the I, to the rectangular form from the polar form. Now this is the magnitude 1.35 the magnitude. This is the cos of the phase difference, and this is the sine of the phase difference. And if we calculate, you can see the I is in the Cartesian form, in the rectangular form. Therefore, we can convert from polar form to the rectangular form very easily, and just like a complex numbers. And you can see the I also having a real part and imaginary part.